So we proved the tree of Tangles theorem last time, and we gave the first of two proofs that I'm going to show you using splinters. We proved that any splintering family has a nested family of elements that represent these sets in the family. So big A1 to big AN have elements little a1 to little an that are nested if this family splinters. And the induction proof said that, well, assuming we have this for n-1, then how do we choose a little an to represent big AN given all the other big AI and given a nested family of little AIs representing them? How do we choose it? Well, we choose it so as to cross as few of the other little AIs that exist by induction as possible, right? So we chose the little an depending on the other little AI that the induction hypothesis handed to us. And then we, in the course of the further proof, we changed all the little AIs. We had carefully adjusted the little an to these given little AIs, and then we changed them all. We're replacing them with corners and so on, keeping this little AI an fixed. So that was the induction step. And then, obviously, if you redo the induction from bottom to top, then when you choose little a n+1, you apply the whole induction hypothesis again, and then you change all the little a I, now I, from 1 to n, once you have chosen that optimally to fit these. So we always change the earlier ones again and again and again, n times, if we want to do n steps altogether. And that was sort of not very efficient. It's the opposite of greedy. Right? We don't keep anything that we have. We choose something new and then change everything that we had before. Just keep reapplying the induction hypothesis several times. Okay. And since that's not my point now. My point now is that we make choices when we come to appoint a little an as a representative of big AN, because there may be many that cross the little AIs as little as possible. So we have to choose one. Now, if you program a computer to do that, then you can't tell it to choose any one. It has a list of all the candidates for little an, and then it goes through the list and takes the first one. Now, that, in turn, has the consequence that if we present our data, the graph, to the computer in a different way, then this list may have a different order. So it might choose a different little an. So as a consequence, any construction that makes choices can give us different results mechanically if we program a computer to execute this proof. Never mind its inefficiency. And so a construction that doesn't make choices, but which is entirely determined by invariants of the thing you're studying, in this case, the graph G, is called canonical. And our second proof of theorem 12.5.1, the tree of Tangles theorem, is going to be canonical. It finds, it doesn't use any choices. I can even name the set of nested separations that it finds. I'll do that in just a moment. And then that's it. So now that I've promised it, I may as well do so, but we'll make it precise later. So the nested set that efficiently distinguishes all the tangles is the following set. For every pair of distinguishable tangles, we take all the efficient distinguishers, all the separations that distinguish these two tangles efficiently, take the union of all these sets over all the pairs of distinguishable tangles, call that big set D. And now, from every set of efficient distinguishers for a given pair, we take all those, not just one, all those that cross as few elements of the big D as possible. Right, so I've given you a lengthy but completely precise definition just now in words. That doesn't make any choices. Formally, making no choices is a little difficult to define unless you do logic and formalize the use of language. So it's customary to replace that definition with the simpler definition, which says that an object constructed for another object, in this case a graph G, is called canonical if the automorphisms of that object, the graph G now, leave that constructed object invariant. So to give you just an example, if you have three tangles that come in the form of three big complete subgraphs and no edges between those three, right? So if n is bigger than 7, you certainly have 3 5-tangles here. Then here's a nested set of separations that distinguishes them all. This is the first one, this Kn versus the other two. There's another one, this Kn versus the other two, and that's enough. If you take any two tangles now, say those corresponding to these two Kns, we can find one of these separations, this one here, that distinguishes those two. But it's not canonical because we chose separations that split off one of the three from the other two for these two, but not for that one. If we added this, it would be superfluous in terms of that theorem, but it would make the tree of tangles canonical. And right, if you apply an automorphism to this graph, the disjoint union of Kn's, you can do that, right? Map each Kn to the next one in cyclic fashion, and then the separations of this graph, of course, map to separations of the image, but this separation here would map to that separation, which would not be in the original set. So the set of tangle distinguishers, the nested set that we chose initially, that just consists of those two, would not be invariant under this automorphism of the graph. And that would violate the practical definition of being canonical. And if you want to do tree decompositions, well, what's the tree decomposition of this first separation, collection of separations? Well, we have this, one separation against the rest, which is this separation here against the rest. So we have something like this. This would be the tree decomposition corresponding to this initial set of nested separations. There's two of them. Here's one, and there's the other. And the correspondence is as in the exercise that you have done by now. Right, and if you want the tree decomposition to be canonical, what does it formally mean in the derived definition? It would mean that the automorphisms of G should act as automorphisms of the tree decomposition. What's an automorphism of a tree decomposition? Well, what do you think it is? You have to have an automorphism of the tree, map the tree to itself, its nodes to its nodes, so that edges map to edges. automorphism of the tree that commutes with the nodes indexing parts. So an automorphism of G that is canonical in this respect should map parts to parts, and it should do so in such a way that the indices of these parts are mapped to each other by this correspondence that make an automorphism of the tree. And that clearly isn't the case here. So the same automorphism of the graph here that just cyclically shifts these Kn does not define an automorphism of this tree here. Because this tree has a middle part, which this tree decomposition has a middle part that cannot be mapped by an automorphism of the tree to either of these side parts here. Okay, so what would be a canonical tree decomposition? Well, if we added this, we'd just get that, right? So we'd now have a 3-star for a tree. This bag here, of course, will be empty, but that's fine. So this will be a canonical tree decomposition. The early one is a non-canonical one. Both satisfy that. Okay, questions? Okay, being canonical is a good thing. It's important not only in practical terms, also theoretically. So these tree of tangles have been used for what's called the graph isomorphism problem, which is a computational problem. You give your computer 2 graphs and you ask it, are they isomorphic? And that's one of these classical problems whose complexity status is still unknown. It's nearly known by now, but one of the main attempts by Martin Grohe that nearly got there in the last couple of years used precisely canonical tree decompositions to approach that. Right, so I think that's all I wanted to say about canonical. So let's do the second proof. The second proof involves another theorem, of which it is going to be a corollary, of which the first theorem is going to be a corollary. And the theorem reads as follows: for every set, curly S, of entanglements in G, the S-friendly separations in G, whatever they are, I'll tell you, of course, meet every S and are nested. So the entanglements will be the sets of efficient distinguishers for a pair of tangles, right? Here's the definition of entanglement. We'll go through it in a moment. But whatever they mean, the point is that the sets, every set that of separations which efficiently distinguish a given pair of tangles, every such set is an entanglement. Right? And now, if that's the case, then this theorem will prove the tree of tangles theorem, right? Because we just take all the S-friendly separations for S, the set of all entanglements. Then this says that these S-friendly separations represent every entanglement. They have every entanglement has a an S-friendly element, and all these S-friendly elements are nested. So we have a nested set of separations that include one from every entanglement. That's it. So I need to tell you what an entanglement is. And that definition is here. So one entanglement. Here we're going to have a set of entanglements. A single entanglement is still a set of separations, such that for each one of them, T, the following holds. So T is a separation. Consider another separation crossing this given element T. Then if we have two corners on the same side of T with the property that they both have orders at most the order of T, then one of them has the order exactly order of T and lies in the set big T in the entanglement. That's an abstract definition. Why is that a sensible definition? No way I can explain that. It's been distilled from countless improved versions of the canonical tree of Tangles theorem. And it sort of encapsulates exactly those properties of crossing separations and corners that are needed in the proof. So it all boils down to these properties, and that's why they've got a name. That's the only reason. They're not natural in any obvious sense, except that they capture what we need in the way of properties to prove the canonical tree of Tangles theorem. And to reassure you, entanglements that are not sets of separations that efficiently distinguish two given tangles, as in our application, do exist. So there are other examples. So the theorem 1258 is stronger also in the set that there are other entanglements than those that we intend for the application. Okay, once more, question about the definitions? No. In that case, let me just prove to you that the efficient tangle distinguishers do always form an entanglement. Right. So suppose T is an efficient distinguisher of a tangle ToR and a tangle ToR prime. Then consider any other separation in G and consider those corners on the same side. We could be considering those. Let's consider these because they're drawn there. And then now let's assume that the order of those corners is at most the order of T. Right, if we assume that, then ToR will have to orient these two corners, right? Because it orients all the separations up to some order. And since it orients T, and the order of those are no bigger than the order of T, it also has to orient those two. How can it orient them? Well, it cannot orient both of them this way because it orients T that way. And that would be a contradiction to robustness, to the property R that tangles have. So it will have to orient one of them at least, in fact, also at most, but at least one of them towards that corner. Yeah, but what does that mean? That means that this corner here also distinguishes ToR, which orients it this way, from ToR prime, which orients T that way, and therefore by consistency, also that corner that way. Remember, consistency is the property that two separations that are nested are not oriented away from each other. So T is nested with this corner, and ToR prime must not orient them away from each other. So since it already by assumption orients T this way, it can only orient this corner that way, differently from ToR. So this corner is a distinguisher of ToR and ToR prime, whose order is at most the order of some efficient distinguisher. So its order cannot be properly smaller. So its order has to be exactly the order of the efficient distinguisher, and that's what we want for the entanglement. Okay? It just clicks into place, but that's no big wonder because that's exactly how this condition E, I haven't given it a name, so I want to call that condition E. Here, that is condition E. That's how that came about. Questions? Okay, so that means that all we need to do now in order to prove the canonical tree of Tangles theorem is to prove this theorem here. Right? Because I've just shown you that the efficient Tangle distinguishing sets of separations do form entanglements, and therefore by this theorem, they will have a nested set of representatives that meets them all, and that will do for this. Right, and you will see that it's canonical because we'll define it precisely. I mean, the definition of S-friendly is going to not involve any choices. Right. If there are no more questions, then I'll wipe this away. Okay. Now we need some lemmas. Okay, one more definition. Given a set S of separations of G, we let X of another separation A count the separations in S that A crosses. So this is, I call it an X, but it's really a cross. Right? So X of little a is any separation in G, is going to be the set of S, I think I want to call them R's. Yeah. Little r in S, such that A crosses R. So this is cross. Without the cross, it would be is nested with. This is any separation of G. All right, so we're going to need that definition later. And now we need three simple lemmas about corners. So the first is 1255. given crossing, I think. Yes. Given crossing separations S and T, given opposite corners C and D of S and T, two things hold. For every separation R. No, let me write it in shorthand. So if R crosses C or D, then R crosses S or T. And the same with and. Okay? So the picture is that we have S and T, and we have opposite corners. And the first is that if a separation, that R is any separation, right? If this crosses S, then it has to cross either T or S. So it can be something like this or something like that, but it can't sort of not cross either of those two. It can't sit in any corner here and single out just a subset here, because then it will be nested with this corner. So if R crosses one corner, then it also crosses at least one of those two. And if it crosses both corners, then it will also cross both S and T. That's the assertion. Right, and the first of them is just the fish lemma. Right, the first says if this crosses one of the two corners, then must cross S or T. Why? Remember the fish lemma? And it says that any separation that is nested with both S and T, so it doesn't cross either one of them. Any separation that is nested with both of two crossing separations, oh, it was there, right, is nested with all four corners. So if this is false, if R does not cross one of them, but is nested with both of them, then it's nested with all four corners, then this is false too. So that's just the fish lemma. And the second, we also use the contrapositive. So suppose R does not cross both. So suppose R is nested with one of them, say with S. Then, since C and D are opposite corners, either side, both sides of S have one of them sitting there. So this side of S has, say, D, or it might have C. So R would be nested also with this D, right? I mean, I've applied to your intuition of nestedness, which of course is completely not allowed, right? You have to use the definition of nestedness. That means there exist comparable orientations, but you just have to write it down and make, say without loss of generality 17 times, and then you have the same thing. So if R is nested with one of them, then, for example, with S, then there exist orientations. Let me draw them like this, where R is bigger than, or R forwards is bigger than S forwards. Then S has these two corners on opposite sides, so there exists a corner, so it's nested with them, and there exists on each orientation of S is greater than a suitable orientation of one of the two corners, and then by transitivity of this partial ordering, you get that R is greater than that particular orientation of D, and so that the two are nested. Okay, you can read it in the book, in the text. It's easy. Okay, so that was a simple lemma. Second simple lemma, 12, 5, 6, S, T, C, D as here. So S and T cross, and we have opposite corners C and D. Then X cross of C plus cross of D is strictly less than cross of S plus cross of T. Right. This is now for a given set of separations, which in 12.5.5 we didn't have. So, and S and T are taken from that set S. Right? And this X then refers to that set S of separation. So the longhand of this would be for every set big S of separations, let X and S and T be two crossing elements, and let C and D be opposite corners, then this inequality holds where X cross refers to this S. So it counts how many elements of big S such a little c or whatever crosses. Right, so let's prove that, and that's really easy. I don't even have to write anything. So let's evaluate little x on all the elements of big S. Okay, give yourself a little r and big S. If r is crossed by C or by D, then it's also crossed by S or by T. And that's the first statement up here. Right? If R crosses C or D, it also crosses S or T. If it counts here, then it also counts there. If it counts twice here, if it crosses both C and D, then it also counts twice here because it crosses both S and T. So every little r in big S corroborates this inequality, albeit weakly. The count here is at most the count there. But then there are two little r's for which the inequality is strict. And those two little r's are S and T themselves. Right? So they are nested with all four corners, obviously. Two crossing separations are nested with their corners. So they count 0 here, but little s counts 1 here, and little t counts 1 here. Okay, so we get strict inequality at the end of the day. Questions? Okay, good. So that's 12.5.6, and now 12.5.7. Now I'm talking about S-friendly separations, and I'll have to tell you what they are. .1257 says that they're nested if some complicated condition holds. Right, before I tell you the condition, let's look at the definition of friendly. Here it is. Let curly S be any set of sets of separations, as usual, like the set of all entanglements of distinguishable pairs of tangles. But now, for theorem 1258, just any set of sets of separations. Then we call another separation which doesn't primarily have anything to do with curly S. We call that S-friendly if now we do relate it to big S, if it is contained in some element S of curly S, for which something else has to hold as well, namely that no other element of that big S crosses fewer elements than little s does. Then little s is called curly S friendly. So little s is optimally nested in some set to which it belongs. That's a short version of it. Okay, then little s is called curly S friendly. And now the condition is the following. For every two elements of curly S, big S and big S dashed, and for every choice of elements of those, for every little s and big S, little s dashed and big S dashed, there exist corners so that one of two things hold. Of S and S prime. Am I assuming that they cross? Yes. Okay, so let me write this differently here. For every right, like this. There are corners of those two such that one of the following is true. So the corners that exist are those two in this case. let's call them C and C prime, and the statement is that C prime is in S prime and C is an S. Okay, so one case is that we have opposite corners in different sets, S and S prime. And the other case is this. Where's my green chalk? Here. That we have one pair of opposite corners in S, and the other pair of opposite corners in S prime. Okay? So these are two outcomes that are allowed. And the statement that if this is the case, if for every choice of a big S and a big S prime, both in curly S, there are corners that satisfy this, or there are corners that satisfy that. If that is true, then the S-friendly separations are nested. Okay. So let's prove that. That's proof of 12.5.7. So we're going to assume all this. Let me make it into a yellow box. So that was a red box. Yeah. Which encroached a little on our newly required space. This red box here define condition E, which we're still going to use, and my yellow box now is the if statement. Right. Assume the yellow box. Suppose there exist S-friendly S and S little prime that cross. So we want to show that they can't cross, that they're all nested. The S-friendly separations are all nested. That's what we want to show. We're assuming this. We want to show that the S-friendly separations are all nested. Suppose not. Suppose there are S-friendly separations that are not nested, that cross. By definition of S-friendly, there exist homes for these S-friendly separations. Remember? Here, that's the first thing it has to claim. It has to claim a home in curly S. So if these two are S-friendly, then there exist elements of curly S. So there exist that contain little s and little s prime, respectively. Okay. Now, let's look at the if condition. The if condition says that if we have such elements of curly S that contain two separations, and now we've established that. We didn't have it earlier. Now we've established that by the assumption that S and S prime are S-friendly. They have homes. Now, given such a situation, there are corners with this or with that. Okay, well, we can assume that. So by assumption, one or two holds. Suppose first that one holds. Right, what does one say? One says that there are opposite corners in S and in S prime. Then we use 12.5.6, which says that when we have two separations, two crossing separations in a given set S, what is the given set S now? Here, this one, that is not this S. This is going to be the union of all the elements of curly S. And then it says that these corners satisfy that inequality. So by 12.5.6, we have x of C is less than x of S. Or x of C prime, the opposite one, is less than x of t, x of S prime. So why is that? It's like an application of submodularity, except with the strict inequality. If this sum is less than that sum, it is not possible that this is at least that and this is at least that. We can choose which ones we compare. So if this is at least that and this is at least that, then this sum is at least that sum, which is not the case. So we know that either this is strictly less than that or this is strictly less than that. So that's what we have here. But this is in big S, and this is in big S prime. So we have a contradiction. We still have the relevant information that C is in the same big S as little s is, but C crosses fewer elements of the entire union of curly S, and therefore it wins the comparison here for little r's against little s. So little s should not be called curly S friendly, all right? Because in this big S, which it claims as its home, there should not exist another separation that crosses fewer elements of union curly S than S does. But there does now exist such a thing. And similarly here, since C prime shows that S prime doesn't satisfy the requirement for being S-friendly, at least not with its claimed witnessing set big S prime. Okay, so that's the proof of, for the case of 1. Now, for 2, let's assume that S, order S, is no bigger than order S prime. So one of the two will hold, so we can assume that. And that only prompts us to now consider these two opposite corners, those that are in S prime. If I had chosen this the other way around, we'd be considering those two. Okay, so applying 12, 5, 6 to these two corners, so x of C prime plus x of D prime is less than, well, less than what? I mean, the x's here. Right. So this sum by 12, 5, 6 is less than x of s plus x of s prime, but x of s is less than x of x prime, so this is less than 2x of s prime. So let's say x of C prime is less than x of S prime, right? And now we have the same contradiction as earlier, because both these are in S prime, and this was claiming to be S-friendly by appointing big S prime as its home in curly S, so that would require it to cross at most as many elements of union curly S than any other element of big S prime, but here we have found another element of big S prime that does cross fewer elements of union curly S, so we have a contradiction again. Okay, questions? No. So that's the proof of 12.5.7. And now we've got all the lemmas, and we can prove the theorem. So what do we have to show? Given any set curly S of entanglements, the S-friendly, curly S-friendly separations are nested. We apply this lemma. The lemma says that the S-friendly separations are nested if this holds. So to prove that, let's give ourselves the situation of the yellow box, and we have to show, we have to find corners of S as in the yellow box, i.e. such that 1 holds or 2 holds. First claim, at least 3 corners when I speak of corners, I always mean corners of S and S prime now, are relevant. And what I mean by relevant, have order at most S prime. Relevant is not a big deal. Having order at most, the larger of the two orders that occur. Right, so by submodularity, when we consider two opposite corners, at least one of them will be relevant. Right, their orders sum to the sum of these orders, and the sum of these orders is at most twice this. Right, so at least one of these has order at most this. So of two opposite corners, at least one of them is relevant. And of these as well. So we can certainly find we can find two adjacent relevant corners. Submodularity adjacent relevant corners. Let me draw them in green. Okay, like here. But then by assumption, unless the claim is true, then the other two must be irrelevant. So these have order bigger than S prime. Now, let's look at this vertical separation. This could be either S or S prime, because I drew the adjacent corners on the right. So if all we know is that they're adjacent corners, they could be on the same side of S, or they could be on the same side of S prime. We don't know that. So this is either S or S prime, the blue thing. So if it's S, then we have a contradiction to this being an element of the entanglement big S, right? Because this says that if we have an element in, this is now little s, an element in the entanglement, and we have two sides, two corners on the same side of this, and we know that both of them have order at most order this, why do we know that? We need submodularity again. So earlier I just said they are relevant and therefore they have order at most S prime. But the other side has order bigger than S prime by assumption that there are at most two relevant corners. So this has order bigger than S prime. So this has order strictly less than even order of S, right, by submodularity. Okay, and if we have this situation, if we have two corners order at most the blue thing, then one of them has order, exactly order of the blue thing and something, but even the first is not true. Right, so we have a contradiction there. And similarly, if this is an S prime, it's even worse. Okay, and the second claim is that all corners are relevant. Now, let's say we're log. we'll log all 4 corners are relevant. Now suppose only 3 of them are relevant, then 2 lie on the same side of S prime. So S prime is the vertical one, and we know that there are at least 3 that are relevant. So 2 of them lie on the same side of S prime. This is C, this is C prime, and we have 2 on the same side of S prime, then one of them has to be good, good meaning these 2 things. Say this one is good, then C prime equals order S prime, and it lies in big S prime. Okay, then the opposite corner has order at most order S, not just order S prime, which is relevant for being relevant, but it has order at most S by submodularity, but the 2 sum to at most order S plus order S prime, and if this uses its allowance, then this cannot exceed its allowance, so it has to have order at most S even, little s. Now, the relevant corners, we started with 2 on the same side. We found this, so now we know that this is in fact relevant. We didn't use this assumption. We didn't know which of these was the 3rd relevant one, but now we know that this is definitely relevant. So if 2 fails, then this will be irrelevant. And if this is irrelevant, so the order is bigger than S prime, then the order here is smaller than little s. We're applying condition E to S. So this is S. Condition E to S. Both these corners have order at most order this. They lie on the same side. So one of them has to have order exactly this and lie in S. So that isn't this corner because this doesn't have order exactly order S. So it must be this. So C lies in S and has order exactly S. But we also knew that its opposite corner, C prime, lies in S prime. So we have found a pair of opposite corners in S and in S prime, and that is condition 1. Okay, so we have proved that all 4 corners are relevant. Questions? No? Good. Now we apply condition E to little s prime. We apply to both sides. So we can find a corner on the left of S prime and a corner on the right of S prime that lie in S prime. So and have order exactly order S prime. So let's first assume that they're adjacent. So we have one on the left, one on the right. That satisfies that. They could be adjacent or they could be opposite. right? So if they're adjacent, they can be here or there. So let's assume they're up there. So this is equal to the order of S prime equal to the order of D. And this lies in S prime, and this lies in S prime. These have order, at most order S, by submodularity. Not only order S, at most order S prime by being relevant, but in fact, by submodularity, order at most order S, because these have order exactly order S prime. So, and now we apply E to the bottom side of little s. These two satisfy that for S now. So one of them has to be in S. But whichever one has to be in S, its opposite corner is in S prime. So we have one again. And the other case is similar. So let's now assume that the corners on different sides of S prime that E returned when we applied it to the two sides of S prime are opposite corners. So these are now C prime and C, say. It could be the other pair of opposite corners. Right, so we know that these are in S prime and have order exactly S prime. Okay, but now we have two opposite corners that both have order, big order S prime. But how does that square with submodularity? It doesn't unless order S equals order S prime. So these both have the maximum of the two. And since they sum to order S plus order S prime, these in fact have to be equal. But now we apply E for the upper side of S. And then either this is in, so all four corners are relevant, all four corners qualify for this now. Right? So this E just tells us which is in which set. So applying E to these two corners tells us that one of these two corners is in S. In S, right? We're applying that to the upper side of S. If this corner is in S, well, then the opposite corner is in S prime, and we have one again. So we may assume that this is in S. But we can do the same down here. One of these two has to be in S, applying E to little s with these two corners. If this is in S, then we have one because this is in S prime. So this is in S. But now we have two. These are in S, those are in S prime, and we have this situation here, and then we're done. Thank you for your patience. Any further questions?